Henry had been watching the temperature gauge drop for 3 nights straight. -40, -43, -46. The plywood cabin he'd built with his own hands was failing him, and not slowly, it was failing him all at once. The way things fail in Alaska when the interior decides it's done tolerating bad construction. He'd caulked every gap he'd find. He'd wrapped the walls in extra vapor barrier. He'd burned through a full cord of birch in less than 3 weeks, and still woke up every morning to a cold that crept back in while he slept. The cabin wasn't losing to the weather. The cabin was losing because of the way it was built. And Henry, sitting by his wood stove that winter with a cup of black coffee, going cold in his hand, finally admitted what he'd known for 2 years. The shape was wrong. Everything about it was wrong. Here's what they don't tell you when you watch a build video or flip through a homesteading magazine. The square cabin, the pitched roof, the plumb walls, the ridge beam, the rafter system. That design was developed for mild climates. It was optimized for rain shedding and summer ventilation in regions where the worst-case scenario is a foot of snow and a hard freeze that lasts 2 weeks. Alaska is not that place. The interior of Alaska is a completely different engineering problem, and the conventional cabin was never the right answer for it. It's just the answer that got repeated, because that's what people knew how to build. Henry knew how to build it too. That was the problem. He'd built it correctly. Square, tight, properly framed, and it still couldn't hold heat at -40. So he started paying attention to what was actually working out there. Not what people were building, what was surviving. And what he kept coming back to, again and again, was the arch. The Quonset hut has been around since 1941. The United States military developed it to house personnel and equipment in extreme environments around the world: Arctic conditions, desert heat, coastal storms. They needed a structure that a small crew could assemble without heavy equipment, that could withstand loads no conventional framing would survive, and that could be packed and shipped anywhere on Earth. What they built was a corrugated steel arch. No load-bearing interior walls. No ridge beam. No rafters. The arch itself is a structure, and it works because of pure geometry. A properly loaded arch doesn't bend. It compresses, and steel and compression is one of the strongest things you can build with. The military built hundreds of thousands of them. They proved themselves in conditions that destroyed conventional buildings. And then when the war ended, the construction industry went right back to selling 2x6 framing and plywood, sheathing, and asphalt shingles, because that's what the supply chain was built around, and that's where the margin was. The Quonset didn't disappear. It got reclassified. It became a farm building, a storage shed, something you park equipment in, not something you live in. That reclassification was not an accident. It was convenient for an industry that had no interest in selling you a kit for $14,000 when they could sell you a full stick frame build for $100,000. Henry saw through it. That winter, he ordered a kit 24 feet wide, 40 feet long, 18-gauge corrugated steel panels, pre-punched and pre-bent, designed to bolt together in an interlocking arch from both sides simultaneously until they meet at the crown. The system doesn't require a crane. It doesn't require a large crew. It requires patience and a torque wrench and the willingness to trust that the geometry is doing what the geometry has been doing for 80 years. Henry had that willingness. What he didn't have anymore was patience for a building that was costing him 7 cords of wood a winter and a set of lungs full of cold air every morning. He started with a foundation in late August because the ground in the interior freezes deep and it freezes early. And if you're not sitting on a footing that goes below the frost line, you're not sitting on a foundation. You're sitting on a slow motion heave that'll crack your slab and rack your walls within 2 seasons. He dug 5 feet down, poured a continuous perimeter footing with 1/2-inch rebar on 16-inch centers, brought up to grade with 8-inch block, parged the exterior face, wrapped the whole thing in closed cell foam board before he backfilled. Then he waited 3 weeks for the concrete to cure, because concrete that hasn't cured is just expensive gravel, and Henry was not going to shortcut the one part of the build that he'd never be able to fix later. The panels arrived on a flatbed, bundled in sets of 12, each panel roughly 4 feet wide and 60 pounds. He had helped the first weekend, his neighbor and the neighbor's kid, who turned out to be genuinely useful. And then he worked alone. You can do this alone. That's the part people don't believe until they see it. Each panel nests into the one beside it. Bolts at every rib with zinc-coated carriage bolts and lock nuts, and the arch rises in a curve that gets more stable with every panel you add. Henry torqued every bolt down with an impact driver, then went back by hand with a wrench, because he'd seen what thermal cycling does to hardware in cold climates. A bolt that's slightly loose in August will be a gap by December. A gap is where the cold lives. He didn't leave it any openings. 4 days of actual work. 9 days of weather windows. When the last crown panel dropped into place, and Henry walked the perimeter of what he'd built, he stopped in front of the old cabin and looked at it for a long time. A collection of right angles trying to argue with a climate that doesn't respect right angles. The Quonset behind him looked like it had grown there. It looked permanent in a way the cabin never had. Now here's where most people building metal arch structures in cold climates make a catastrophic mistake. And it's a mistake that gives Quonsets a bad reputation in northern regions. They skimp on the insulation system. Or worse, they approach it the same way they'd approach insulating a wood frame wall. Fiberglass bats between furring strips. A vapor barrier stapled to the inside face. Done. And then they wonder why the building sweats. Why the interior temperature swings 40 degrees between morning and evening. Why the steel is dripping condensation in February. Here's the physics. Steel conducts heat approximately 300 times more efficiently than wood. That's not a slight difference. That's a different category of material behavior entirely. If you put warm, moist interior air against cold steel, you will get condensation. Every time. The question isn't whether you'll get it. The question is where. And if you get it inside your insulation assembly, inside the wall cavity, behind the furring strips, you won't know it's happening until it's already ruined something expensive.
Henry did not make this mistake. He had a spray foam crew come in before he touched a single furring strip. 2 inches of closed-cell polyurethane applied directly to the interior face of every steel panel, from the base of one end wall to the base of the other, continuous and unbroken. No gaps, no seams, no thermal bridges. The foam bonds to the steel and becomes the vapor barrier, not a sheet of poly stapled to framing, but a chemically bonded layer that the moisture physically cannot get behind. That 2 inches of closed-cell foam is also R13 by itself, and it changes the thermal behavior of the steel completely. The surface the interior air sees is no longer metal at -40, it's foam at a manageable temperature. Then he built a secondary wall, metal stud grid, offset 8 inches from the arch panels, mineral wool bats filling the cavity, total insulation assembly, approximately R40. That's more than most code-built houses in Alaska carry in their walls. And Henry's wall is a continuous arch with no thermal bridges, no framing penetrations, no place for the cold to find a shortcut. He spent more money on that insulation system than most people spend on an entire shed. He does not regret a single dollar. The floor came next. 4-inch reinforced concrete slab over 6 inches of compacted gravel and 2 inches of rigid foam board between the gravel and the concrete, because a slab sitting directly on frozen ground in interior Alaska is a cold floor that no amount of rugs will fix. Radiant tubing runs through the slab, connected to a propane boiler that functions as backup heat. The primary source is a large catalytic wood gasifier against the north end wall. Henry ran the numbers, BTU output against volume and insulation values, and arrived at a figure that still surprises him when he thinks about it. On a still day at -30, his gasifier can maintain 68 degrees inside with a fire that would have barely touched the old cabin at -10. He finished the interior over the following spring and summer, tongue-and-groove white spruce on the secondary wall framing and on the ceiling grid, fir strip flooring in the living section, sealed concrete in the work area, a bathroom with a composting toilet and a gravity-fed shower off a 500-gallon tank, a kitchen built around a 2-burner propane stove, and open shelving of rough-cut alder milled from a blowdown stand 2 miles up the ridge. He left 3 feet of exposed arch at the crown, raw steel foam-coated and visible, because he wanted to be able to look up and see exactly what was holding the building up. He thought it was important not to forget. November of that first winter, a cold snap hit that took the thermometer to -52. The weather station in town stopped reporting wind chill because the instruments maxed out. Henry fed the gasifier at 10 in the evening, banked the fire, and went to sleep. He woke at 6 in the morning to an interior temperature of 68 degrees. He checked the gauge twice because 30 years of living in bad buildings had conditioned him to distrust good numbers. The gauge said the same thing both times. He sat with his coffee and didn't say much. He didn't need to.
People asked him now what it cost. He tracked it all. The steel kit was just under $14,000 delivered. Foundation materials, concrete block, rebar, foam board, a little over $9,000. Spray foam insulation with labor for $1,800. Interior framing, mineral wool, and finishing lumber, $6,000. Mechanical system spread over 2 years, roughly $11,000. Total, fully functional, fully insulated, off-grid capable, in interior Alaska, $45,000. He priced a comparable stick frame build with contractors the same winter he started planning. Lowest quote he received was $88,000. Highest was $112,000. Both of those builders had assumptions baked into their pricing that didn't account for the real cost of working in that climate, in that location, in winter. Henry put those numbers next to 45 and stopped having doubts. He'll tell you honestly what the Quonset doesn't do well, because he's not selling anything. The curved walls limit where you can push furniture. Storage has to be designed around the arch profile, rather than against flat surfaces. Running electrical requires more planning than stud bays allow. He solved all of it. Custom shelving that follows the curve, surface-mounted conduit in the work area, wiring routed to the secondary framing in the living section. But those problems existed, and the solutions took time. He wants you to know that going in, because a building that surprises you with problems you weren't expecting is worse than a building whose problems you understood before you started. The second winter was harder than the first. 3 weeks in January where daytime highs didn't clear -35 and the nights went lower. Henry burned 4 cords for the entire season. In his old cabin, during a milder year, he burned more than 7. He kept a written log the whole time. Interior temperature, exterior temperature, wind speed, daily wood consumption. The data isn't calibrated to laboratory standards, but it's consistent across 2 full winters. And what it shows is a building that performs at a level the old cabin couldn't approach regardless of what he threw at it. The old cabin is still standing 10 yards away. He uses it for tool storage. He hasn't torn it down. He looks at it sometimes from the window on cold mornings, with the coffee going warm in his hands and the interior of the Quonset holding steady at whatever he set the gasifier to the night before. That view, the old shape against the new one, the wrong answer standing next to the right one, does something that no-cost spreadsheet fully communicates. It makes the decision feel final, settled. He built the right thing. He built it 30 years later than he should have, but he built it, and out here, in this climate, in a place where the margin for error is exactly 0, working is everything. Working is the whole thing, and the arch works. The construction industry will tell you that modern materials are better. In some ways, this is true. The coatings are more sophisticated. The fasteners are more precisely engineered. The computational tools for structural analysis have capabilities that the Quonset point engineers could not have imagined. None of this has produced structures that routinely outlast what those engineers built with corrugated steel and geometry, and the pressure of necessity bearing down on every decision they made. Necessity clarifies. It removes the option of complexity for its own sake. It drives you toward the essential, toward the thing that actually works under the conditions you actually face, without the luxury of adding expensive solutions to problems that a better fundamental design would have prevented in the first place. The Quonset was a product of necessity applied to engineering intelligence. What became, over 50 years, was a product of that foundation maintained by human attention. Neither element was sufficient alone. Together, they produced something that confounded every expert who looked at it with expectations shaped by construction culture that had stopped believing in the arch volcano finished clear in the doorway and stood for a moment in the opening, looking back at the interior. The wood stove glowed in the far corner. The tools hung in their order on the iron hooks. The wood pile stood in its precise stacks against the curved wall. The arch overhead caught the firelight and distributed it evenly through the space, the curve doing what curves do, gathering, redirecting, making the most of what was given to it. He had stopped trying to explain the hut to people who were not prepared to hear it, not because the explanation was difficult, but because the explanation required the listener to accept something that modern building culture resisted, that the engineers who worked fastest under the most pressure with the fewest resources in the middle of a catastrophic war had understood something fundamental about structure and honesty and the relationship between a building and the forces it would face. And that understanding had produced something more durable than anything the subsequent decades of prosperity and technological advancement had managed to replace it with. The arch did not care about modern building codes. The corrugations did not care about current material specifications. The gravel pads did not care about what the permit application said about foundation requirements. The galvanization did not care about replacement cycles or warranty periods or the construction industry's financial interest in buildings that needed to be torn down and rebuilt within a generation. The physics did not care about any of it. The physics just worked the way physics always works. Quietly, consistently, without drama, producing the same results every time the same conditions were met. Volkov had met the conditions. He had done it for 30 years. He picked up the shovel again. There was more snow at the door. There was always more snow at the door. He went back to work, the amber light at his back, the cold ahead of him, and the arch holding above it all exactly as it had always held. Steadily, without complaint, and for longer than anyone who had not paid attention would have thought possible.